something is deeply wrong with the night sky, and almost nobody notices it. Look up on a clear night and you see thousands of stars scattered across the dark. Beautiful, peaceful. But here is the problem. The universe contains more stars than grains of sand on every beach on Earth, burning in every direction across billions of years. By every calculation, the night sky should be completely, blindingly bright. Not dark, not scattered pinpoints of light. Uniformly, totally bright. But it isn't. The sky is dark, almost completely, perfectly dark. That one quiet contradiction turns out to be one of the deepest mysteries in the history of science. And the answer is not what anyone expected, because what the darkness above you is quietly hiding will completely change the way you see the universe. Now get yourself comfortable, hit subscribe. We begin. Step outside on a clear, moonless night, far enough from the city that the sky opens fully above you, unfiltered, unlit, raw. Look up. Notice what your eyes register first. Not the stars, not the constellations, not the faint smear of the Milky Way crossing overhead. The darkness, an overwhelming, pressing, almost physical blackness that surrounds every point of light and fills the space between every constellation with something that feels closer to absence than to sky. The stars are there, yes, cold and bright and scattered across the dome above you, but they are outnumbered, profoundly outnumbered. For every pinpoint of light, the darkness surrounding it stretches endlessly in every direction, and that precise, unsettling ratio of light to dark is the question this entire story orbits. The universe is full of stars. We know this. We can prove this. And yet standing beneath it, what you feel, more than anything else, is the dark. The first thing to do is resist the easy answer. The easy answer exists. Most people accept it without question, and it is not wrong. It is simply nowhere near the full truth. The easy answer goes like this. The sky is dark at night because the sun has rotated away from our side of the planet. We are in Earth's shadow. Direct sunlight cannot reach us, and so darkness follows. That part is accurate, and it explains almost nothing about the real mystery. Buried inside that easy answer is a harder one that most people never stop to ask. Because Earth's shadow, the mechanics of a rotating planet, accounts only for why your side of the planet is not receiving sunlight from our local star. It says nothing about the universe, nothing about the hundreds of billions of other stars that exist entirely apart from our sun, radiating in every direction, across billions of light years, for billions of years. And so the real question, the one that matters, is this. Why, in a universe filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, does their combined light not fill the night sky with something other than blackness? To approach that question, we first need to understand what the daytime sky is actually doing. Consider daylight. Not the sun itself, but the sky surrounding it. The deep blue dome above you on a clear afternoon. Look in any direction other than at the sun, and the sky is still bright. Light seems to arrive from everywhere at once, as if the air itself has been set softly on fire. And that raises a question most people have never stopped to ask. Why does the entire daytime sky glow, rather than just the small disk of space where the sun actually sits? The answer lives in the atmosphere. Every layer of air above us is not simply empty space. It is a layered mixture of molecules, mostly nitrogen and oxygen, along with tiny suspended aerosols, microscopic water droplets, and fine particles of dust. When sunlight pours into this mixture, the light does not simply pass through undisturbed. At every collision with a particle small enough, smaller than the wavelength of the light itself, the light scatters. It deflects outward in all directions from every collision point, like a ripple spreading from a pebble dropped into still water, except the ripple is made of light, and those collisions happen millions of times between the sun and your eyes. This process carries the name Rayleigh scattering, named after the British physicist Lord Rayleigh, who published the mathematics describing it in 1871. And Rayleigh scattering has a remarkable and decisive preference. Not all colours of light scatter equally. Visible light is a spectrum. Red light travels in long, slow waves. Blue and violet light travel in shorter, faster ones. And Rayleigh's equations revealed that shorter wavelengths scatter far more powerfully. Blue and violet light scatter roughly 9 to 10 times more efficiently than red light when bouncing off atmospheric molecules. 9 to 10 times. Think of it this way. Imagine throwing two different stones through a dense field of hanging wind chimes. A small, light stone catches every chime, deflecting sharply sideways at each encounter. A large, heavy stone pushes through most of them and continues mostly forward. Blue and violet light behave like that small stone, bouncing sideways at every molecular encounter, arriving at your eyes from nearly every direction across the sky. Red light pushes through with far fewer deflections and continues in its original direction. The sky appears blue not because space is blue, not because the air contains blue pigment, but because blue photons ricochet off countless molecules and arrive at your eyes from everywhere above you, while red photons travel more directly onward. The entire daytime sky glows because the entire atmosphere has become a vast, continuous scattering machine. The same logic explains sunsets. When the sun sinks near the horizon, its light must travel a far longer diagonal path through the atmosphere to reach your eyes, up to about 40 times longer than the direct overhead route. Imagine the difference between a short hallway and an extraordinarily long corridor made of the same air. In the long corridor, blue and violet light have vastly more opportunities to scatter away before arriving. What survives that extended passage is the light that resisted scattering most stubbornly. The longer wavelengths, the reds, the oranges, the amber golds that burn across the western sky. The atmosphere has never been a window, always a painter. Now here is where the story sharpens into something genuinely important, because Earth is not the only world we can study. We have sent spacecraft across the solar system. We have photographed the skies of other worlds from their surfaces, and those photographs expose something that should shift, fundamentally, how you understand what you're seeing when you look up. The Moon has essentially no atmosphere. Its surface pressure approaches what scientists describe as a hard vacuum, so vanishingly thin that sunlight arrives at the surface having met almost nothing on the way down. The photographs from the Apollo missions show astronauts standing in full blazing sunlight, and the sky above them is perfectly, completely black. Not dim, not shadowed. Black, the way a sealed room with no light source is black. The sun hangs there, burning intensely, and directly beside it, the sky is as dark as open space, because without atmosphere, nothing scatters. Without scattering, there is no sky. Shadows on the Moon are ferociously sharp. One side of a rock blazes white, the other plunges into absolute black, with no soft gradual transition between them. On Earth, our atmosphere acts as a vast diffuse lamp, filling every shadow with redirected photons arriving from all directions. Remove the atmosphere, and shadows become razor blades. Mercury tells the same story. The world closest to the Sun, where sunlight arrives at roughly 6 to 7 times the intensity that reaches Earth's surface, and yet beneath that intensity, the sky above Mercury is black. Then Mars. Mars carries an atmosphere, approximately 1% as dense as Earth's, mostly carbon dioxide, laden with fine iron-rich dust that stays suspended for months at a time. The result is a sky that glows muted reddish-orange during the Martian day, not from Rayleigh scattering, but from those larger dust particles interacting with sunlight differently from atmospheric molecules. And Mars delivers something unexpected: blue sunsets. When the Martian sun drops toward the horizon, its light travels a longer path through the dust-laden air. The red wavelengths scatter away. What remains near the sun's disk, as confirmed by NASA's Curiosity and Perseverance rovers in photographs taken directly from the surface, is a pale, ghostly blue, an alien twilight that is the precise reverse of our own. Venus pushes further still. Its atmosphere is roughly 92 times denser than Earth's at the surface, wrapped in continuous cloud layers of sulfuric acid extending across the entire planet. Sunlight never focuses into a sharp disk at all. The Venusian sky glows uniformly bright in every direction, featureless, shadowless, a white dome of diffuse light where the sun cannot be located, only vaguely sensed as a brighter smear somewhere within the glare. 4 worlds, 4 entirely different skies, black, reddish-orange with a blue twilight, uniformly white, and not one of them shaped by what lies beyond the atmosphere. Every single one of those skies is produced entirely by local conditions, by whatever chemistry, density, and particle content happens to sit above each surface. The cosmos behind each atmosphere contributes nothing to the color overhead, which means the color of Earth's daytime sky, the deep blue dome we have stared at every day of our lives, has nothing to do with what the universe behind it actually looks like. The blue is ours. The glow is local. When we look at the daytime sky, we are not seeing the cosmos. We are watching our own atmosphere perform its quiet optical art on every photon that passes through it. And at night, when Earth rotates and carries us away from the sun, when the scattering that fills our days with warm, diffuse light grows thin, when the atmosphere thins to something closer to a transparent window, the actual universe presses through, not painted, not scattered, not transformed by local chemistry, and the actual universe is dark, not slightly dark, not dimly lit, under the clearest, darkest conditions, from high deserts or remote mountain peaks far from any city glow. The naked human eye can resolve approximately 5,000 individual stars across the entire visible sky. 5,000 points of light, distributed across a dome spanning 41,000 square degrees, an area equivalent to roughly 200,000 full moons arranged side by side. Those 5,000 stars are islands. The ocean between them is black. But here is what most people don't realize. Those 5,000 stars are not the universe. Our Milky Way galaxy alone contains hundreds of billions of stars, too distant and faint for unaided human eyes to detect. And beyond our galaxy, across the observable universe, astronomers estimate somewhere in the range of 2 trillion galaxies, each containing hundreds of billions of their own stars, all of them burning, all of them sending light outward in every direction through space for billions of years, toward us, and the sky is dark. Think about that for a moment. That should feel wrong, and the reason it feels wrong is because, mathematically, it is wrong. It is one of the most serious and profound observational puzzles in the entire history of astronomy. A universe of that density, that age, and that luminosity should not produce a dark sky. And the reason it does is one of the most beautiful and disturbing answers science has ever arrived at. Look again at those gaps between the stars, not the bright points. Look at what surrounds them, that darkness, the silence pressing in from every direction around every constellation. We have always assumed it meant nothing. A background, the empty part, the space between the things that matter. But that darkness is not empty. Something is written there in the apparent absence of light. Something about the age of the universe, the speed of light, the geometry of space itself. Evidence we have been staring at for our entire existence, without once recognizing what it was. Before we can begin to read it clearly, though, there is something unexpected we need to address. Because some of the darkness you think you recognize in famous photographs of space, the black sky above Apollo astronauts, the void surrounding spacecraft in orbit, the emptiness behind distant planets, may not mean what you think it means. And if we mistake that kind of darkness for the real thing, the deeper mystery becomes nearly impossible to solve. Some of the most famous photographs in history show a black sky above sunlit astronauts on the moon. No stars, no distant galaxies, no pinpoints of light anywhere in the frame. Just the astronauts, their equipment, the blazing grey surface. And above it all, a sky as dark and absolute as a sealed room with no light source. For decades, some people have pointed at those black skies as evidence of something wrong. The stars should be there, they say. Space should be full of light. The absence of stars proves the photographs were staged. But that conclusion gets the science exactly backwards. Those black skies are not evidence of deception. They are evidence of something far more interesting. And once you understand it, it will change what you think you are looking at every time you glance at any photograph of space. Let's be precise about what a camera actually does. At its most basic level, a camera is a machine for collecting light. And like any collection process, it requires time. The moment a shutter opens, light begins arriving and accumulating on the film or sensor inside the camera. The moment the shutter closes, collection stops. Whatever light arrived during that controlled window gets recorded. Whatever arrived in quantities too small to register above the detector's background noise, those faint signals vanish as if they were never there. That controlled window of time is called the exposure. Nothing more complicated than that. Exposure is simply how long the camera allowed light in. Think of it like a bucket left out in the rain. A bucket left out for 10 seconds collects some water. A bucket left out for 10 hours collects a great deal more. Both collected rain from the same sky. But the 10-second bucket missed most of what fell. A camera works the same way. Longer exposure, more accumulated signal. Shorter exposure, less. And every photographer, every engineer, every imaging scientist faces the same inescapable trade-off. A very short exposure captures bright subjects cleanly, but leaves faint ones invisible. A very long exposure reveals the faint, but in doing so, floods and destroys every bright source in the same frame, turning it into a featureless, washed-out blur. No camera, at any point in history, has been able to do both simultaneously. Now, let's put the Apollo photograph specifically into focus. The lunar surface in full sunlight is intensely bright, roughly comparable to a sunlit scene on Earth, minus any atmosphere to soften or scatter the incoming light. The astronauts' white spacesuits were designed to reflect solar radiation efficiently, making them among the most reflective objects in the entire frame. NASA engineers, working with the Hasselblad cameras the astronauts carried, prescribed precise exposure settings in advance, a shutter speed of 1/250th of a second, with an aperture of f11 for sunlit areas and f5.6 for regions in shadow. These are standard, sensible settings for a brightly lit outdoor scene. Any photographer covering a beach on a sunny afternoon would use similar values. The problem is what those settings mean for the stars. The faintest stars visible to the naked eye under the darkest possible conditions arrive at roughly 10 billion times less light than the sun delivers. 10 billion times less. Even Sirius, the brightest star in the nighttime sky, is so far below the exposure threshold needed for sunlit astronauts that it would require an exposure many thousands of times longer just to begin to register. Fainter background stars would need exposures of minutes, distant galaxies, hours. At 1/250th of a second, those stars were simply not there for the camera. They existed. The photons were arriving, but in the fraction of a second the shutter was open. So few of those photons reached the film that they drowned without a trace in the detector's background noise, the unavoidable faint hiss of thermal energy that every light-sensing surface produces, which drowns out any signal too faint to overcome it. Stars never had a chance, but even setting shutter speed aside, a deeper constraint was at work. Every image, every single photograph ever taken, captures only a slice of the available brightness. That slice has a name: dynamic range. The term sounds technical, but the concept is immediate and personal. Dynamic range is the distance between the dimmest thing a given image can record and the brightest thing it can record without losing all detail. Anything brighter than the top of that range gets recorded as pure white, a washed-out blank, stripped of all information. This is called saturation, the equivalent of filling a container past its capacity and having everything above the rim simply spill away. Anything darker than the bottom of the range gets recorded as pure black, indistinguishable from absolute darkness. On the lunar surface, with sunlit astronauts and reflective suits and blazing grey regolith, the dynamic range needed to capture the foreground correctly was already extreme. The difference between the deepest shadows and the brightest highlights in those frames was staggering. The camera was pushed to its limits just handling what was in front of it. Stars, arriving at 10 billion times less intensity than the sunlit surface, sat so far below the bottom of that range that they might as well have been sending no signal at all. Now compare this to how your own eyes handle the same problem, because this comparison is essential. The human visual system continuously adapts. Your pupils contract in bright light and expand in dim light, physically changing the amount of incoming energy. Your retina contains two entirely different populations of light-sensing cells: cone cells, optimized for bright, detailed, colorful daytime vision, and rod cells, tuned for extreme sensitivity and near darkness, capable of responding to individual photons. Your brain, meanwhile, runs a constant background process of adaptation, reweighting what it considers bright and what it considers dark, based on the current lighting environment. Walk from bright sunlight into a dim corridor, and you are essentially blind for a few seconds. Then shapes emerge as your visual system shifts its range downward to reveal what was previously invisible. Walk back into the sunlight, and the glare overwhelms you until your system shifts back. You are not seeing more light in the corridor. The room has not changed. Your perception has shifted, retuning itself continuously to reveal different parts of the brightness spectrum. A camera fixed at one exposure setting cannot do this. A camera is permanently committed to one slice, and the astronauts' cameras were committed to the slice that showed what they had gone there to document. That is the complete explanation. No conspiracy, no cover-up, simply physics and the mathematics of light collection. But here is where the story opens into something larger, because everything described so far is specific to bright subjects, to photographing sunlit astronauts, planets in daylight, spacecraft surfaces gleaming in solar radiation. What happens when you remove all of that? What happens when you point a camera away from every bright nearby object, away from planets, away from stars in our own galaxy, away from anything close, and aim it instead at a patch of sky that looks, to every existing survey, like empty darkness? What happens when you leave the shutter open, not for 1/250th of a second, but for 10 full days? In December of 1995, an astronomer named Robert Williams, then director of the Space Telescope Science Institute in Baltimore, the institution responsible for managing the Hubble Space Telescope, made a decision that some of his most senior colleagues actively opposed. He spent 10 consecutive days of Hubble observing time assigned to him as personal discretionary allocation to use entirely as he judged best, staring at a carefully selected patch of sky in the constellation Ursa Major, near the handle of the Big Dipper. The patch was chosen for one overriding reason: Nothing was there. No bright stars, no known nearby galaxies, no structure visible in any previous survey. The field had been selected specifically because it looked, by every available measure, empty. His colleagues considered it an extravagant risk. Time on the Hubble Space Telescope remains among the most competed for resources in all of science. Thousands of proposals competing for hundreds of available hours each year. Using 10 days of that time staring at what appeared to be an unremarkable void struck many as scientifically reckless. Between December 18th and December 28th, 1995, the telescope completed 150 orbits of the Earth while gathering 342 separate exposures of that same tiny patch of sky. When those exposures were combined and processed, the astronomers examining the result went quiet. The apparently empty patch of sky was full, nearly 3,000 galaxies, not stars, galaxies, each containing hundreds of billions of their own stars, were hiding in a region of sky so small that the entire Hubble Deep Field spans roughly 2.6 arc-minutes on a side. That measurement needs a translation. Imagine a tennis ball held at arm's length. Now move that tennis ball back, further, until it sits 100 meters away from you, roughly the length of a standard athletic track. The angular size of that distant tennis ball, as seen from where you stand, is approximately the size of the Hubble Deep Field. That tennis ball-sized patch of apparently empty sky contained 3,000 galaxies, and that patch represents roughly 1/24 millionth of the total sky above us. Williams had been right. His colleagues had been wrong. Not slightly wrong, dramatically wrong. What the Hubble Deep Field revealed is not simply the discovery of some distant galaxies. What it revealed is the nature of the darkness itself. Every dark patch of sky you have ever looked at, every gap between the visible stars, every direction where your eyes found nothing and concluded nothing was there, is populated. The apparent emptiness is not absence of content. It is the limit of what biological eyes, evolved to navigate a human-scale world in ordinary lighting, can perceive without assistance. Faintness is not the same as absence. These are two entirely different things. A whisper is not silence, a distant light is not darkness, and a sky that appears dark to unaided human vision is not a sky without sources of light. The Hubble Ultra Deep Field, observed in 2004, pushed this further, revealing around 10,000 galaxies in a comparably sized patch of sky. The James Webb Space Telescope has since found galaxies from still earlier in cosmic time within these same tiny regions. Every direction astronomers have looked, with sufficient patience and sensitivity, contains galaxies. Every direction. And still, the night sky is dark. Here is the collision that now must be faced directly. We have established that the apparent darkness of famous space photographs is a photographic artifact, a consequence of exposure and dynamic range, not evidence of an empty cosmos. We have demonstrated that the empty patches of sky are full of galaxies invisible to unaided human eyes. Every direction in the night sky, it appears, leads eventually to a galaxy containing hundreds of billions of stars. The darkness between the stars is not empty. The gaps are full of things we cannot see. And yet, and this is the problem that does not dissolve no matter how carefully you examine the photography, no matter how well you understand dynamic range or biological sensitivity, if every direction truly contains galaxies, if hundreds of billions of galaxies, each containing hundreds of billions of stars, are all sending light outward in every direction through space, the night sky should not be dark at all, not merely brighter than it is, blazing, wall-to-wall light arriving from every direction simultaneously. That is what physics, at least a certain understanding of physics, demands. So why isn't it? Saying the sky looks dark because our cameras are limited, or because our eyes cannot detect faint sources, that explanation is gone now. We know the galaxies are there. We have photographed them, and they are still not filling the sky with light. This puzzle is centuries older than the Hubble Space Telescope. Astronomers working by candlelight were already losing sleep over it. They called it, in various forms, the riddle of the dark night sky, and one name from the 19th century eventually stuck. Understanding why they found it so disturbing, why it seemed to shatter the entire foundation of how they imagined the universe to be built, is the next part of this story. This puzzle is older than telescopes, older than any photograph, any spacecraft, any instrument humanity has ever aimed at the sky. The riddle of the dark night sky was already troubling serious thinkers 400 years ago, and every one of them, working from different countries, different centuries, different traditions, arrived at the same uncomfortable wall. A wall built not from ignorance, but from logic. Pure, careful, inescapable logic, applied to what seemed like the most reasonable picture of the universe imaginable. And that logic said, clearly and without exception, the sky above you cannot be dark. The fact that it is dark anyway is not a minor discrepancy, a rounding error, a detail to be tidied up. The darkness overhead, once you follow the mathematics, becomes evidence that something fundamental about the classical picture of the universe must be wrong. The question is, which assumption, because there are several, reality is forcing us to abandon? For most of human intellectual history, the universe made sense in a specific and reassuring way. Eternal, existing without beginning or end, always having been, always to continue. Static, not expanding, not contracting, not changing in its overall structure. Infinite, extending in every direction without boundary, without edge, without a wall at which space stopped. And populated, reasonably uniformly throughout all that infinite volume, with stars. Stars scattered through space the way grains of sand might be scattered across an infinite floor, more or less evenly distributed, with roughly the same density in every direction, at every distance. This was not an unreasonable picture. For centuries it was, in fact, the dominant scientific framework. Luminaries, including Isaac Newton, operated within some version of it. The universe was ancient, it was vast, it was full of stars, and it extended forever. What could be more straightforward? And from within that framework, a disturbing question arose. A question whose answer, once carefully worked through, produced a result that no one who accepted the model could explain away. Imagine standing at any point in this infinite, eternal, star-filled universe. You are the observer. Space extends outward from you in every direction, filled uniformly with stars as far as geometry can reach. Now, divide that surrounding space into a series of thin spherical shells, like the layers of an onion, but extending outward from you in all directions. The innermost shell is close, the next shell is slightly further away, then another, further still. Each shell has the same thickness. Each shell, by virtue of being further from you, has a larger surface area, and therefore encloses a greater volume of space. Here is the critical calculation. Let's put it into plain language. As shells get further away, the number of stars each shell contains grows. At twice the distance, the shell's surface area is 4 times larger, so it contains roughly 4 times as many stars. At 3 times the distance, 9 times more stars. The number of stars per shell increases with the square of the distance from you, but brightness fades with distance too. A star twice as far away delivers only 1/4 the light. At 3 times the distance, 1/9 the light. This relationship, the inverse square law of brightness, is one of the most fundamental patterns in physics. Think of a campfire. The heat and light warming your face at 1 meter drops to 1/4 of its intensity at 2 meters, to 1/9 at 3 meters. Same fire, same output, but spread over an ever-widening sphere of space, the intensity per unit area falls rapidly. So here are the two effects operating simultaneously. Move to a more distant shell, 4 times more stars, but each star 4 times fainter, 4 times as many, each 4 times dimmer. The extra light and the reduced brightness cancel each other exactly. Every shell, regardless of distance, contributes approximately the same total amount of light to the sky above you. Let that settle for a moment. Every shell contributes the same total light, and an infinite universe contains infinitely many shells. Stack them outward without limit. 1,000 shells, 1,000,000, 1,000,000,000, stretching forever in every direction, and each one adds another equal contribution to the sky's accumulated brightness. Infinite shells, each contributing equally. The sum does not converge. The sum does not approach some comfortable, modest, faint value. The accumulated brightness mathematically grows without bound, and even setting aside the diverging sum, a sharper argument reaches the same conclusion through a different route. Stars are not mathematical points. They have physical size, a surface, a disk that occupies a finite angular area in the sky. As stars get further away, each individual stellar disk gets smaller, subtending a tinier angle. But the number of stellar disks at that distance increases at exactly the same rate, double the distance. Each disk covers 1/4 the angle, but there are 4 times as many disks. The total angular coverage from each shell remains the same. Extend this reasoning across infinitely many shells, and the angular coverage of the entire sky eventually adds up to 100%. Every direction you look terminates on the surface of some star. And here is the final, unavoidable piece. A stellar surface, the glowing outer layer of a star, has a specific surface brightness. The sun's surface, for instance, glows at a particular intensity per unit of angular area. That surface brightness does not diminish with distance. A star twice as far away covers 1/4 the angular area, but delivers 1/4 the light. The same brightness per unit angle. Move it to any distance, and its angular footprint in the sky has exactly the same brightness it would at any other distance, as long as nothing absorbs the light in between. The apparent size shrinks. The brightness per unit angle stays the same, so every direction in the sky should terminate on a stellar surface, and every stellar surface should appear as bright as a stellar surface, which means the entire sky, in every direction simultaneously, should glow at roughly the brightness of a typical stellar surface, roughly the brightness of the sun. That is not the sky we observe. The most human way to feel this is through a different image entirely. Imagine standing inside a forest, not a sparse woodland with open clearings and distant horizon. A truly dense, truly endless forest extending equally in every direction, without boundary, without edge, without a last tree. Every direction you look, you see trunks, branches, bark. The trunks of nearby trees are large. The trunks of distant trees are small, but the forest keeps going. The nearby trees are few, the distant trees are many, and every sight line, no matter where you aim your eyes, eventually strikes a trunk. No sight line escapes. Darkness between the trees is impossible if the forest never ends. Not merely unlikely, geometrically impossible. You might look between the nearest trees and see more distant ones, and between those see more distant ones still, but the gaps keep filling, and in an infinite forest, they always fill completely. Replace tree trunks with stellar disks. Replace the depth of a forest with the depth of an infinite universe. The geometry is identical. Every gap between nearby stars is filled by more distant stars. Every gap between those is filled by stars further still. An infinite, uniform stellar population guarantees that no line of sight escapes to empty space. The darkness between the stars, those gaps we looked at in the first moments of this journey, should not exist. Not in an infinite, eternal universe. This is the paradox in its most direct form. The sky you see above you is dark. The sky you would see inside an infinite, eternal, uniformly populated universe of stars would not be dark at all. It would blaze as brightly as the surface of a star in every direction, with no gaps, no relief, no darkness anywhere. The classical universe predicts something radically, catastrophically different from the sky that exists. One of them must be wrong. Either the sky is wrong, which it is not, we can measure it, or the universe is wrong. And if the universe is wrong, then one or more of those seemingly reasonable assumptions is false. The universe is not infinite, or not eternal, or not static, or not uniformly filled with stars, or some combination. But something in that classical picture of the cosmos does not match reality. The dark sky is not a neutral fact. The dark sky is evidence. The disturbing thing about this paradox is not that it was recently discovered. The disturbing thing is how old it is, and how long it waited for a satisfying answer. In 1576, the English astronomer Thomas Diggers published a cosmological model featuring an infinite universe populated with infinite stars, and asked, almost immediately, why those stars did not together fill the sky with overwhelming light. He could not answer the question he had raised. In 1610, Johannes Kepler, one of the greatest mathematical astronomers who ever lived, stared at the same problem. Responding to Galileo's newly published report that a telescope revealed tens of thousands of stars invisible to the naked eye, Kepler wrote plainly, "If this is true, and if they are suns having the same nature as our sun, why do not these suns collectively outdistance our sun in brilliance?" Kepler used this very darkness as scientific ammunition. For him, the dark sky proved the universe must be finite, a bounded island of stars surrounded eventually by empty space. The darkness was not a puzzle to be explained, it was a boundary to be inferred. Around 1718, Edmund Halley, the astronomer whose name now rides a comet across our sky every 75 years or so, revisited the calculation and pressed it further. In 1744, the Swiss astronomer Jean-Philippe de Chezeaux formulated the shell argument in its most mathematical form, arriving at the same unsettling result. And then, in 1823, a German amateur astronomer named Heinrich Wilhelm Olbers published an essay titled On the Transparency of the Universe in a widely read astronomical journal, laying out the paradox for a broad scientific audience in a way that reached more readers than any previous treatment. The paradox did not originate with him. He was not the most mathematically sophisticated of those who wrestled with it, but his name, by a quirk of historical memory, became the one that stuck. Let's call it what the scientific community calls it now, Olbers Paradox. Here, though, a careful distinction deserves attention. Infinity alone is not sufficient to produce the paradox. A universe could be infinite in size and still have a dark sky under the right conditions. What the paradox requires is not just spatial infinity, it requires eternal duration and sustained luminosity. A universe of infinite space but finite age would have a hard boundary in time. Light from stars beyond a certain distance would simply not have had enough time to arrive yet. The shells at extreme distances would contribute nothing to today's sky, because their light has not yet reached us. Similarly, a universe where stars live only finite lives, burning out and going dark after billions of years, would eventually accumulate a population of extinct stellar remnants rather than an endless supply of perpetually burning lamps. The classical model assumed all three: infinite space, infinite time, eternal, uninterrupted stellar luminosity. Strip away any one of those assumptions, and the paradox begins to dissolve. Which one does reality strip away? That is the question that generations of astronomers tried to answer, and the first answers they reached were wrong. Not slightly wrong. Confidently, elaborately, creatively wrong. The most intuitive solution was also the most immediate. If too much starlight is reaching us, perhaps something between us and the distant stars is absorbing it, blocking it, intercepting it before it arrives. The universe, perhaps, is not transparent. It contains clouds of dark material between the stars, soaking up the light from infinitely many distant suns. The darkness is not the absence of starlight. The darkness is the presence of something blocking it. This was a reasonable thought, and it was wrong in a way that took careful reasoning to reveal, a way that shows exactly why a paradox this deep cannot be dismissed with any simple mechanism. The problem runs all the way to the foundation of how energy works, and no amount of intervening material, however opaque, can make the accumulated energy disappear. The most tempting solution to any problem is the one that matches what you can already see, and when astronomers looked at the night sky searching for something that might explain the darkness, they found it immediately, or so they thought. Clouds of dark material between the stars, dust, visible evidence, right there in the Milky Way, of matter that blocks light. If the universe is full of this material, perhaps the light from infinitely many distant stars never reaches us at all. Perhaps the darkness isn't the absence of stars. It's the presence of a cosmic curtain stretched across the intervening space, absorbing everything beyond a certain distance. This was a reasonable idea, a logical idea, an idea supported by visible, measurable evidence, and it was wrong in a way that makes the paradox significantly deeper than it first appears, because the reason it fails is not a minor technical objection. The reason it fails is a law of physics so fundamental that nothing in the observable universe can circumvent it. Before examining each proposed solution in turn, the framework needs to be clear. Olbers Paradox is not asking why the night sky is slightly dimmer than predicted, or why a few directions in the sky appear darker than expected. The paradox asks why the accumulated light from an infinite, eternal universe, from infinitely many shells of stars, each contributing equally, does not produce a sky blazing at stellar surface brightness in every direction simultaneously. Any genuine resolution must account for the full scale of what is missing, not a small adjustment to the calculation, a complete change in where the accumulated light went, or why it never arrived. That is the bar each proposed explanation must clear, and every solution tried within the framework of an eternal, static universe failed to clear it. Interstellar dust genuinely exists. Standing under a dark sky and looking toward the center of the Milky Way, the dark rifts and lanes, regions where dense clouds of dust and gas block the light of stars behind them, are visible to the unaided eye. This is not hypothetical. The dust absorbs light passing through it. Astronomers have measured this absorption precisely. Certain regions of the sky appear dark, not because stars are absent, but because a dense enough cloud of material stands in the way, intercepting photons before they reach us. So the instinct to invoke dust as a solution to the paradox is completely understandable. Olbers himself proposed something like this, that the darkness of distant space might owe to material absorbing and intercepting the otherwise overwhelming flood of starlight. But here is the problem. A problem that John Herschel, son of the astronomer William Herschel and one of the most rigorous scientific minds of the 19th century, identified as a fatal flaw not long after Olbers' paper appeared. Energy cannot be destroyed. That is not a philosophical statement. It is the first law of thermodynamics, one of the foundational constraints governing every physical process in the universe. When dust absorbs a photon, the photon's energy does not vanish. The energy is transferred to the dust grain itself, raising its temperature. A warmer grain then radiates. It emits energy outward, mostly at longer wavelengths in the infrared range, the same way any warm object glows. A brick warmed by sunlight radiates heat. A piece of metal heated by a torch glows red, then orange, then white as temperature climbs. The energy changes form, the energy changes wavelength, but the energy does not disappear. Now extend this into an eternal universe. Dust that has been absorbing starlight continuously, without interruption, for an infinite length of time, would not remain at the modest temperature of interstellar space. Over time, the accumulated energy heats it, and in an eternal universe, with no beginning to the process and no end to the incoming starlight, the dust would eventually reach thermal equilibrium, with the radiation bathing it. At equilibrium, the dust radiates exactly as much energy as it absorbs. The curtain begins to glow, and at full equilibrium the dust glows as brightly as the stellar surfaces whose light it has been absorbing. The dust screen becomes a dust surface, radiating at stellar temperatures. Dust changes the wavelength of the radiation. Dust changes its direction. Dust does not change the energy budget. The paradox survives completely intact. Perhaps then the universe is not actually infinite in all directions. Perhaps stars occupy a finite region of space, a bounded island in the cosmos, beyond the edges of which lies genuinely empty darkness. Lines of sight aimed past the last stars would encounter nothing. No stellar surfaces to terminate on. No accumulated contribution from infinitely many shells. This was, in effect, the solution that Kepler himself preferred in 1610, a finite universe of stars embedded in surrounding emptiness. And mathematically, within the classical framework, it works. A finite stellar distribution means finite total light. The shells of stars eventually stop. The sum converges. But here is what deep observations revealed. Astronomers have not found an edge. In every direction pointed by our most powerful telescopes, across every patch of sky examined with sufficient sensitivity, from the original Hubble Deep Field to the subsequent Ultra Deep Field, to the expanded surveys conducted by the James Webb Space Telescope, galaxies appear throughout the entire observable volume of space, not concentrated in a central island, not thinning toward a boundary, distributed through the cosmos in all directions as far as any instrument has ever probed. The universe, as best we can measure it, does not have a wall around its stellar population, and distinguishing between what we can observe and what actually exists matters here. The boundary of our observations is not the same as a physical edge of the universe. Our observational horizon is a consequence of how far light has had time to travel, a limitation imposed by time, not by geography. No observation has found the literal last galaxy, the final star, the outer wall beyond which space is empty, and none of the deep field surveys supports the picture of a finite stellar island surrounded by void. That explanation too fails to account for what we observe. Another avenue seemed more promising. Stars are not randomly scattered, they cluster into galaxies. Galaxies cluster into groups. Groups cluster into clusters, clusters into superclusters, superclusters into the vast filaments and sheets of the cosmic web. Perhaps this hierarchical structure, this progressively larger architecture of clustering, means that at very large scales, the effective density of stars thins out indefinitely. Perhaps the universe is a fractal, structured at every scale, and the infinite shells calculation fails because the assumption of uniform density is simply wrong. The cosmic web is real, revealed by large-scale galaxy surveys, including the Sloan Digital Sky Survey, which has mapped the positions of hundreds of millions of galaxies across a significant fraction of the observable universe. The large-scale structure of the cosmos is genuinely extraordinary. Vast filaments of galaxies stretching across hundreds of millions of light-years, like the threads of an enormous three-dimensional web. Between them, enormous voids, regions of space that are genuinely underdense, containing far fewer galaxies than the average. The universe is not uniformly smooth at the scales humans can observe directly. Structure is real, and it is remarkable, but structure has limits. Those same surveys that revealed the filaments and voids also revealed that at sufficiently large scales, once you average across enough volume to sample the full statistical distribution, the universe smooths out. The clustering does not continue indefinitely. The density does not thin forever towards zero. At the larger scales, the universe approaches statistical homogeneity, roughly the same number of galaxies per unit volume regardless of direction or location. The fractal does not go all the way down. The hierarchy has a ceiling, an endlessly thinning fractal distribution with density decreasing at every scale does not describe the observed large-scale universe. The clumping is real. The clumping is also finite in its extent. One more candidate presents itself, deceptively intuitive. Simply this: stars at great distances are so enormously faint that they effectively contribute nothing to the sky's brightness. Common sense suggests that sufficiently distant stars, dimmed by the inverse square law to vanishingly small intensities, would be swamped by the noise of empty space and simply fail to register. But we already ran this calculation. The inverse square dimming is exactly cancelled by the increasing number of stars per shell. At twice the distance, each star is 4 times fainter, but 4 times more stars exist at that distance. The contributions cancel precisely. Each shell adds the same total light. Distant dimming does not rescue the classical model, because the mathematics built that dimming into the framework from the beginning. The cancellation is not an approximation or a rounding error. The mathematics is exact. Distance alone does not explain the darkness. Distance dimming was already accounted for in the calculation that produced the paradox. Stars are not eternal. Our sun has been burning for roughly 4.5 billion years, and in another 5 billion years or so, it will exhaust its hydrogen fuel, swell into a red giant, and eventually collapse into a quiet white dwarf. Every star in the universe follows some version of this arc: ignition, evolution, extinction. No star burns forever. This matters. A universe where stars continuously exhaust their fuel and go dark should over time lose luminous sources. The accumulated light would decrease as more and more stars reach the end of their lives. Perhaps the darkness is simply the residue of a stellar population in the process of burning out. But here is the problem with this reasoning in the context of an eternal universe. A universe without beginning means a universe with no first generation of stars. New stars form continuously from collapsing clouds of gas and dust, just as old stars die. In a universe that has existed forever, stellar birth and stellar death have been occurring forever, producing, at any given moment, a statistical mixture of young, middle-aged and elderly stars, but always maintaining a populated sky. Finite stellar lifetimes reduce the brightness of any given star, but in an eternal universe the population continuously renews. The accumulated problem returns. Finite lifetimes matter enormously for the real solution, but finite lifetimes alone, without finite cosmic history, are not enough. Consider what every one of these explanations has in common: dust, adding material to intercept the light; a finite stellar island, adding a boundary around the stars; hierarchical clustering, adding structural irregularity to the density; distance dimming, invoking a mechanism already embedded in the failed calculation; finite stellar lifetimes, reducing individual stellar output without limiting the total duration. Every one of them accepts the classical universe as given, infinite, eternal, static, and then attempts to bolt a secondary mechanism onto it that reduces or intercepts the light before it arrives. Every one of them leaves the underlying model intact and tries to modify the outcome with an added element, and every one of them fails, not for different reasons, for the same reason. In an infinite, eternal universe, no mechanism that merely intercepts, redirects, or temporarily reduces light can permanently eliminate the energy. Energy poured into the universe without beginning, for infinite time, cannot be made to disappear by anything inside that universe. Dust radiates. Boundaries contradict observations. Clustering has a ceiling. Dimming cancels out. Dying stars are replaced. The problem is not the light's path to us. The problem is the assumed nature of the universe itself. The value of watching these explanations fail is not that it leaves us stranded. It is that it tells us exactly where to look for the real answer. Every failed solution failed because it preserved the eternal universe while trying to suppress the consequence of eternity. The consequence of eternity is infinite accumulated light. No mechanism inside an eternal universe eliminates that consequence. The only way to eliminate infinite accumulated light is to eliminate the infinite accumulation. And the only way to eliminate the infinite accumulation is to make the accumulation finite, which means the universe cannot be eternal. The universe must have an age, a beginning, a moment before which no light was accumulating, because the universe did not yet exist, or existed in a form that produced no starlight. This is not a small modification to the classical model. This is the replacement of a foundational assumption, not patching the calculation, abandoning one of its premises entirely. The darkness between the stars resists every attempt to explain it by adding something to the classical picture. The darkness can only be explained by removing something from that picture, and what must be removed is the assumption that the universe has shone forever. Here is the question that actually resolves the paradox. Not what blocks the light, not how thin does the stellar distribution become at large distances, but how long has the light had to accumulate? If the universe has a finite age, if some definite amount of time has elapsed since the first stars ignited, then no matter how many stars exist, the total amount of light they have collectively emitted is finite. The shells at great distances have not yet had time to contribute. The most distant regions of the universe are not sending us their present light. They are sending us their ancient light, light from earlier, simpler, younger stages of cosmic history. And beyond a certain distance, they are sending us nothing at all, because not enough time has passed for their light to cross the intervening space. But to accept a universe with a finite age is to accept a universe with a beginning, a universe that did not always exist in its current form, a universe that was born, evolved, and has not yet reached old age. That conclusion, fully absorbed, is one of the most unsettling and extraordinary things cosmology has ever established about the nature of reality. The evidence for that beginning, and what it implies for the darkness of the night sky, is exactly where this story leads next. The question that unlocks the darkness is not about what blocks the light, not about how stars are distributed, not about the properties of intervening material. The question is simpler and more profound than any of those. How long has the universe been producing light? Because if the answer to that question is not forever, if the universe has an age, a beginning, a moment before which no stars burned and no light accumulated, then the paradox dissolves. Not by hiding the light, not by reducing the number of sources, but by making the total accumulated light finite, regardless of how many galaxies exist, or how far space extends in every direction. The universe does have an age. Measurements from ESA's Planck satellite, and confirmed by the Atacama Cosmology telescope in Chile, have pinned it to approximately 13.8 billion years, with a precision that a generation ago would have seemed impossible. That number contains the answer to one of astronomy's oldest questions. But first, it demands something that takes a moment to fully absorb. Light travels at a speed that is fast beyond any ordinary human intuition, but it is not infinite. Light moves through empty space at approximately 299,792 kilometers per second, or about 186,000 miles per second. That speed is so far beyond anything in everyday human experience that it barely registers as a finite quantity. In 1 second, light could circle the entire Earth more than 7 times. In 8 minutes, it crosses the distance from the Sun to us, here on Earth. And yet, in the context of the universe, that speed is a strict, immovable limit. Nothing carries information faster. No signal, no force, no influence of any kind can outrun light through empty space, which means that every observation we make, every photograph we take, every signal our instruments receive, carries a delay built into it by the travel time of light. When we look at the Sun, we see it as it was 8 minutes ago. When we look at the nearest star beyond our Sun, Proxima Centauri, roughly 4 light-years away, we see it not as it is right now, but as it was 4 years ago. The light arriving at our eyes tonight left that star while events were happening on Earth 4 years in the past. That delay is the key to everything. Here is the extraordinary consequence of light's finite speed. Every time we look further into space, we are not merely seeing further away, we are seeing further back in time. Deeper distance is earlier history. Every additional light year of distance is another year of look back, another year into the past from which the arriving photons departed. The Andromeda Galaxy, our nearest large galactic neighbour, sits roughly 2.5 million light-years from us. 2.5 million years. The light we see from Andromeda tonight left that galaxy when the earliest members of the Homo genus were just beginning to chip stone tools on the savannas of East Africa. Modern humans did not exist. Written language was 2.5 million years in the future. That is not the Andromeda Galaxy we see. It is the Andromeda Galaxy's past, frozen in transit across an ancient sea of space. And Andromeda is, on the cosmic scale, essentially next door. Look further. The most distant galaxies in the Hubble Deep Field were sending that light toward us when the universe was less than 1 billion years old, when our galaxy was young, when the stars in it were a different generation, when the universe itself looked nothing like what surrounds us today. The further we look, the earlier the era we observe. Distance and time are bound together in a way that has no equivalent in any human experience of geography. The observable universe, the sphere of space from which light has had enough time to reach us during the universe's 13.8 billion year history, forms a boundary around us, not a wall in space, a wall in time. Beyond a certain distance, no light has had time to cross the intervening space and arrive. Regions beyond that boundary exist, most likely, but their light has not reached us yet. They remain, for now, invisible, not because they are absent, but because the universe is not old enough to have delivered their signals to our instruments. Consider, for just a moment, where you are right now. Whatever light is falling on you, from a screen, a lamp, a window, cross the distance from its source to your eyes in a fraction of a nanosecond, effectively no delay at all. But every photon you have ever seen from the night sky has been in transit for some portion of the universe's history. Some of those photons left their sources before written language existed, some left before Earth existed, and some, from the most distant galaxies, left when the universe was a fraction of its current age, when almost nothing yet resembled the cosmos we inhabit now. Every act of looking at the sky is an act of archaeological time travel, and the deeper the look, the older the light. This is where the classical model's fatal flaw becomes fully visible. That model assumed every shell of space, near and far alike, contained the same population of fully formed, eternally burning stars, radiating steadily throughout infinite time. But that assumption is simply wrong, and the wrongness becomes more severe with every increase in distance. The shells closest to us contain stars and galaxies we recognize, mature, fully assembled, similar to the cosmos we inhabit. But look further. The galaxies at greater distances are younger, smaller, less structured, still assembling. The universe at earlier epochs was a less developed place. The stars were younger generations, the galaxies less evolved, the structures less defined. Continue further. Reach distances corresponding to 1 billion or more years after the Big Bang, and the galaxies become rare, irregular, primitive, nothing like the grand spirals and ellipticals that populate our neighborhood today. Continue further still. Approach cosmic dawn, the epoch when the first generation of stars ignited. These were the population 3 stars, so called because they formed from purely primordial material, almost entirely hydrogen and helium, with trace amounts of lithium, forged in the first minutes after the Big Bang itself. No carbon, no oxygen, no iron. Elements forged in stellar cores had not yet been made. These first stars were likely massive, hot, short-lived, burning through their fuel rapidly before dying in violent explosions. The universe was, at that moment, learning for the first time what it meant to shine. And before them, before the first stars, the universe passed through what astronomers call the cosmic dark ages. Not a metaphor, a literal description, a period beginning roughly 380,000 years after the Big Bang, when the universe had cooled enough for electrons to combine with atomic nuclei for the first time, and extending for perhaps the first 100 million years or more, during which no stars existed anywhere. The universe contained matter, vast clouds of hydrogen and helium gas, slowly cooling, slowly gravitationally collapsing toward the density needed to ignite the first stellar cores. But no light source had yet switched on. No star was burning. The universe was dark. Imagine a cosmos with no illumination at all, not the soft darkness of a moonless night filled with starlight, but the genuine absence of any luminous object, anywhere, in any direction. A universe lit only by the faint glow of its own cooling background radiation, stretching into wavelengths too long for any eye to see. The dark ages lasted until the first stars ignited, pulling matter together with gravity, compressing hydrogen until nuclear fusion began. At that moment, the first true light in the history of the cosmos, the universe's clock for accumulated starlight started. But that clock started only about 100 million years or so after the Big Bang. Not infinitely long ago, not eternally, recently in cosmic terms. Before the Dark Ages, the universe was not merely dark. Before 380,000 years after the Big Bang, the universe was a hot, dense plasma, matter so energetic that electrons could not remain attached to atomic nuclei. Photons could not travel freely. The entire early universe was opaque, like looking into the interior of a star, not because anything blocked the view, but because the medium itself would not allow light to propagate freely. Every photon was immediately scattered, reabsorbed and re-emitted. The universe had not yet become transparent to its own light. When the universe cooled enough for electrons to finally combine with protons into stable hydrogen atoms, at approximately 380,000 years, photons could suddenly travel freely for the first time. That ancient light still exists. We detect it today as the cosmic microwave background, the faint afterglow of that moment of first transparency. But that boundary, 380,000 years after the Big Bang, is the absolute furthest any electromagnetic signal can reach us from. Beyond it, in look-back time, nothing has travelled to our instruments. The plasma wall is the back of our observable universe. Here is what this means for Olbers Paradox, stated as directly as possible. The classical model assumed each shell of space contributed equal accumulated brightness from eternally shining stellar populations. The outermost shells contain not eternal stars but the cosmic dark ages. Further still, not even the dark ages. A plasma wall through which no photons have travelled. The assumption of eternally shining stellar populations throughout infinite distance is not approximately wrong. Not slightly wrong. The farthest directions contain epochs before a single star existed. The accumulated light is not infinite. The accumulated light has been building for at most 13.8 billion years, and at great distances, for far less, because earlier epochs had fewer stars, smaller galaxies, shorter stellar lifetimes. The total starlight ever produced by the observable universe is a finite quantity, and a finite quantity spread across the entire sky produces a sky that is, exactly as we observe, dark. This is the central resolution of Olbers Paradox. Not dust, not clustering, not boundary walls around a finite stellar island. Time. The finite age of the universe means the light from infinitely many stars has not had time to reach us. The shells of space that exist far beyond what we can observe have not contributed their starlight to our sky because their light is still in transit, still crossing the vast distances between them and us. Depending on where those regions of space are, and how space itself has been expanding during that transit, their light may never arrive. And here is a subtle point worth holding carefully. Spatial infinity is still possible. The universe may well extend beyond our observable horizon, in all directions, without limit. An infinite universe is not what the paradox disproves. The paradox disproves an eternal universe, one without beginning. A universe of infinite space but finite age produces a dark sky, because finite time means finite accumulated light, regardless of how much space exists beyond our observational reach. The darkness between the stars is not evidence that the universe is small. The darkness between the stars is evidence that the universe is young. Finite age is the central answer, but not the only one, because even among the light that has had sufficient time to travel toward us, even among the photons from stars that have been burning long enough, in galaxies close enough for their light to have crossed the distance, something else has been happening during that transit, something that further reduces the energy of those photons before they arrive, something that has been operating on every photon crossing the cosmos since the Big Bang, stretching them, weakening them, shifting them toward wavelengths that carry less energy with every passing moment of their journey. The universe, it turns out, has not been static while that light was traveling, and what the universe has been doing to the space those photons move through changes what arrives at our eyes in a way that goes beyond mere distance. Every photon crossing the cosmos on its way to our eyes is making that journey through something that has not been standing still. The space between its source and us, the medium through which it travels, has been changing since the moment the photon departed, expanding, stretching, growing larger with every passing moment, and as the space stretches, the photon riding through it stretches too, its wavelength pulled longer, its energy drained, its color shifting toward frequencies our eyes cannot reach. By the time that photon arrives, it may carry only a fraction of the energy it launched with, and some photons, from sources far enough away, will be so thoroughly drained that no instrument our biology provides could ever detect them. This is the second major reason the night sky is dark. Not only has the universe not shone forever, the light that has been produced is also being quietly robbed of its energy, across billions of years of transit, by the very expansion of space that carries it toward us. Let's be precise about what we mean by cosmic expansion, because the intuitive picture most people carry is subtly wrong in a way that matters. Expansion is not galaxies flying outward through pre-existing static space. like debris from an explosion hurtling through empty air. That image implies a center, an edge, a direction. The actual phenomenon is different and stranger. Space itself is growing. The geometry of the universe, the fabric of space-time, is stretching at every scale simultaneously. Galaxies are not moving through space towards some cosmic horizon. The space between them is simply becoming more of itself, as if the medium through which they sit is continuously inflating. The mathematics describing this comes from Einstein's general relativity, his framework for understanding how mass, energy, and the geometry of space-time interact and evolve. Within that framework, the universe need not have a center or an edge to expand. Every point in space can be moving away from every other point simultaneously, the way every raisin in a rising loaf of bread moves away from every other raisin as the bread itself grows. Not because the raisins are falling through the air, but because the bread surrounding them is expanding. In 1929, the American astronomer Edwin Hubble published his observation that distant galaxies showed a systematic shift in their light, a shift toward longer, redder wavelengths. And the further away the galaxy, the larger the shift. Hubble's measurement established what cosmologists now call the velocity-distance relationship. The recession of galaxies scaled with their distance in a way that pointed to a universe not merely large but growing, a universe in motion, a universe with a history and a beginning. The shift in the light from distant galaxies is called redshift. The name describes exactly what it is. The observed wavelengths of light are shifted toward the red end of the spectrum, toward longer, lower energy wavelengths, compared to what was originally emitted. But here is the crucial distinction that separates cosmological redshift from the more familiar Doppler shift you might encounter in everyday life. The Doppler shift, the drop in pitch of a passing ambulance siren, the change in the sound of a passing vehicle, comes from an object moving through a medium. The source moves, and the waves it emits get compressed in the direction of motion and stretched behind. Cosmological redshift is different at its root. The source is not moving through space. The space itself is stretching, and as it does, the wavelengths of light, traveling through it, are stretched proportionally. Think of drawing a wave on a rubber band, and then stretching the rubber band. The wave doesn't change because the rubber band moved. The wave changes because the material it is drawn on has been physically extended. Cosmological redshift works in precisely this way. Every wavelength of light crossing the expanding universe is being physically elongated, continuously, throughout its entire journey, and the consequence is immediate and measurable. A photon emitted by a distant galaxy with a particular wavelength, say, ultraviolet light, carrying high energy, invisible to human eyes because its wavelength is too short, arrives at Earth with its wavelength stretched into the visible range. We see it as blue or violet light, having never known it started as ultraviolet. Look at a galaxy even further away, and light that departed as visible blue arrives as red. Further still, and originally visible light arrives in the infrared, wavelengths too long for human eyes, detectable only by specialized instruments. Every step of additional distance means more stretching, more energy drained from every photon. A source that should appear bright becomes, through expansion alone, dimmer than simple distance would predict. The cosmic microwave background, the ancient thermal afterglow of the early universe, is the most vivid demonstration of this effect anywhere in nature. That radiation was released when the universe was roughly 380,000 years old, when temperatures had finally cooled enough for electrons and protons to combine into stable hydrogen atoms. At that moment, the universe became transparent to light for the first time, and photons flooded outward freely. The temperature of that radiation at the moment of release was approximately 3,000 degrees, similar in character to the surface of a dim star, glowing in visible wavelengths. That radiation has been traveling through expanding space for approximately 13.8 billion years, and in that time, the wavelengths have been stretched by a factor of roughly 1100. The original 3000-degree glow has been pulled and elongated into microwave wavelengths, invisible to human eyes, cold, faint, filling the sky in every direction at a temperature of just 2.7 degrees above absolute zero. 2.7 degrees. The coldest light in the universe was once hot enough to glow. This is what expansion does to light over cosmic timescales. Not a modest dimming, a transformation so complete that the radiation is no longer recognizable as the same phenomenon that departed its source. Expansion contributes a second effect that compounds the dimming further. Not only does each photon arrive with less energy than it left with, the photons also arrive less frequently than they departed. Picture a distant galaxy emitting photons toward us at regular intervals, 1 photon per second of that galaxy's own time. But as those photons travel toward us through expanding space, the space between successive photons is also expanding. The gap between photon 1 and photon 2 grows as both travel. By the time they arrive, the interval between them is larger than the interval at which they were emitted. The galaxy appears to be running in slow motion, not because time is passing differently for it in any absolute sense, but because expanding space is stretching the interval between signals just as it stretches the wavelengths of the signals themselves. This effect, cosmic time dilation, has been directly confirmed in observations of distant supernovae. Events that last a certain number of days in nearby galaxies appear to last proportionally longer in very distant ones, stretched by exactly the factor that expansion predicts. The dimming from a distant source in an expanding universe is not just from the inverse square law. The reduced photon energy and the reduced photon arrival rate combine to dim sources far beyond what distance alone would predict. The universe's expansion is not merely moving galaxies apart. It is actively suppressing the light they produce from reaching us at full strength. By the late 1990s, 2 rival teams of astronomers were racing to answer a question cosmologists had spent decades asking: how fast was the universe's expansion slowing down? Gravity, after all, should be pulling everything back toward everything else. The expansion from the Big Bang should be decelerating over time, like a ball thrown upward gradually surrendering to gravity. The question was how quickly, and whether gravity might eventually bring the expansion to a halt. To measure this, both teams used a particular type of exploding star, called a Type 1a supernova, that always reaches approximately the same peak brightness. By comparing how bright a distant supernova appeared with how bright it should be at that distance, they could measure whether expansion had been faster or slower in the past than it is today. Both teams fully expected to find the universe slowing down. Saul Perlmutter's supernova cosmology project at Lawrence Berkeley National Laboratory, Brian Schmidt and Adam Rees's High-Z supernova search team, competing, checking each other's work using the same basic method. Both had assembled dozens of carefully measured distant supernovae. In 1998, both teams published their results, and both results said the same impossible thing. The distant supernovae were fainter than expected, not because the expansion was slowing, but because the expansion was speeding up. The universe was not decelerating under gravity. Somehow, at some point in cosmic history, the expansion had begun to accelerate. Something was pushing it faster, something that pervades all of space, carries no apparent mass, and counteracts gravity at the largest scales. No one had expected this. Scientists named that something dark energy, not because it is dark in any visual sense, but because it remains almost entirely unknown. Dark energy appears to make up roughly 2/3 of the total energy content of the observable universe, based on current measurements. Yet physicists have no satisfying explanation for what it fundamentally is, where it comes from, or why it has the strength it appears to have. One of the most dominant constituents of reality, confirmed by two independent teams using the most careful measurements available, remains a label on a mystery. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011 for the discovery. The mystery of dark energy remains completely open. The accelerating expansion does something else, something that transforms the nature of cosmic darkness from temporary to permanent. In a universe where expansion was slowing, almost all the light produced anywhere would, given enough time, eventually reach us. Distant photons traveling toward us would always be gaining ground, because the rate of expansion that opposes them would be decreasing. Given unlimited time, nearly everything would eventually arrive. But in a universe where expansion is accelerating, the situation changes fundamentally. Some regions of space are receding from us faster than light can cross the intervening distance, and with acceleration, those regions recede faster with every passing moment, not slower. A photon emitted from such a region today begins traveling toward us, but as time passes, the expansion of space between the photon and us grows more rapidly than the photon can cross it. The photon makes progress for a while, then it loses ground, then it loses ground faster. Eventually, it never arrives. Astronomers call the boundary separating the reachable from the permanently unreachable the cosmic event horizon. Beyond it, any signal emitted now or ever cannot reach us, no matter how long we wait. Currently, the cosmic event horizon sits at roughly 16 billion light-years away, about 16 billion times the distance that light travels in a year. Anything beyond that distance has already issued its last signal to us. Not its last visible signal, its last signal of any kind. New light, new information, gone. This is a profound shift from what the classical model assumed. Olbers Paradox was, at its heart, a problem about accumulation. The idea that given enough time, starlight from every direction would accumulate until the sky was blazing. The resolution through finite age already limited that accumulation. Expansion reduces it further by draining energy from every photon in transit, and the cosmic event horizon eliminates it entirely for the most distant regions. The darkness between the stars is not waiting to be filled. In an accelerating universe, portions of that darkness are permanent, not a gap that will eventually close as more distant light arrives, a gap sealed by the geometry of space itself, by the nature of dark energy, by the mathematics of accelerating expansion. Those regions of the cosmos are, for all practical physical purposes, gone from our future. The darkness overhead is not a temporary state awaiting more starlight. For the most remote regions, the darkness is the final answer. And yet, even understanding all of this, there is one more layer to the darkness that we have not addressed. All of this reasoning has been conducted within a specific limitation, the assumption that the relevant radiation crossing the cosmos is radiation human eyes can detect, visible light, the narrow slice of the electromagnetic spectrum our biology evolved to perceive, but the universe does not restrict its radiation to wavelengths that happen to match the sensitivity, range of the human retina. The cosmos is filled with radiation at wavelengths our eyes cannot see at all. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. Wavelengths both far longer and far shorter than what registers as light to us. When we say the night sky is dark, we mean it appears dark to human eyes. What the universe actually looks like, across all its wavelengths, is a different story entirely. And that story contains a surprise that changes what we mean when we say the sky is dark in the first place. The sky appears dark. We have spent this entire journey examining why, the finite age of the universe, the stretching of light by expansion, the permanent inaccessibility of regions beyond the cosmic event horizon. All of that is real. All of that matters. But every argument so far has rested on an assumption so deeply embedded in how we perceive the world that we have barely noticed it. The assumption is this, that when we say the sky is dark, we mean something objective, something that would be true for any observer, any instrument, any being anywhere in the universe, that the darkness we see is the darkness that exists. And that assumption is wrong. The sky only appears dark within a specific narrow range of wavelengths, the range that human eyes happen to detect. Outside that range, the universe is not dark at all. The night sky is full of light, ancient light, energetic light, radio whispers and X-ray screams, and the oldest glow in existence, all of it crossing the cosmos simultaneously, passing straight through your eyes without registering as anything. The darkness, to a significant degree, belongs to the observer. Let's examine precisely how narrow that range is. All electromagnetic radiation, all light in the physicist's sense of the word, exists on a continuous spectrum. Radio waves at one end, with wavelengths as long as a building, carry the lowest energy. Gamma rays at the other extreme, with wavelengths smaller than an atomic nucleus, carry the highest. And stretched across the vast range between them at every wavelength in every direction, from every source in the universe, radiation travels. Human eyes detect wavelengths from roughly 380 nanometers to roughly 700 nanometers. A nanometer is 1/1000th of a meter, about 10 times the diameter of a single atom. That 320 nanometer wide window, from deep violet to deep red, is what we experience as all the color in existence, the entire visible spectrum, every shade of every sunset, every star color, every shade of blue in every sky. According to measurements from the US Department of Energy and NASA, that visible window represents approximately 0.0035% of the full electromagnetic spectrum. Not 1%, not a fraction of 1%, a fraction of a fraction of a percent. If the full electromagnetic spectrum were a stretch of road running from one end of Earth's equator to the other, roughly 40,000 kilometers, or approximately 25,000 miles, the portion human eyes can see would cover a distance of about 1.5 kilometers, about the length of a long bridge. The rest of that road is invisible to us, and the rest of that road is full of light. In 1964, 2 radio engineers at Bell Telephone Laboratories in Holmdel, New Jersey, were testing a newly built horn-shaped antenna designed for satellite communications. Arno Penzias and Robert Wilson were careful, methodical scientists, and they had a problem. Their antenna was picking up a persistent background hiss, a faint, uniform radio signal arriving from every direction in the sky with equal intensity. Penzias and Wilson checked everything. They verified their equipment. They recalibrated their instruments. They even found a pair of pigeons nesting inside the antenna horn and removed them, carefully cleaning away the material the birds had deposited. The hiss remained. They removed the pigeons again. The hiss remained. Every direction they pointed the antenna, north, south, east, west, up toward the zenith, the signal was there, equally strong, completely uniform. Only after contacting colleagues at Princeton University did they understand what they had been hearing. The persistent hiss was not noise from their equipment, not interference from city lights, not residual radiation from nuclear weapons testing. The faint, uniform radio signal arriving equally from every direction in the sky was the oldest light in the observable universe, the thermal afterglow of the first moment the cosmos became transparent to radiation, released 380,000 years after the Big Bang, when the universe cooled enough for electrons to combine with protons into stable hydrogen atoms for the first time, and photons were finally free to travel. Penzias and Wilson had accidentally discovered the cosmic microwave background. The Nobel Prize followed in 1978, and what their antenna had been detecting, that persistent, uniform, inescapable hiss, fills the entire sky, in every direction, at this moment, as you read these words. The cosmic microwave background represents the universe's most ancient radiation. At the moment of its release, the matter temperature measured approximately 3,000 degrees, comparable to the surface of a cool red star, radiating light in the orange-red range of the visible spectrum. But that radiation has been traveling through expanding space for roughly 13.8 billion years, and the expansion has stretched its wavelengths by a factor of approximately 1100. What began as orange-red stellar surface light has been stretched into microwave wavelengths, arriving today at a temperature of approximately 2.73 degrees above absolute zero. If human eyes were sensitive to microwave wavelengths instead of visible light, the night sky would look nothing like what we see. Every direction overhead would glow with a faint, nearly uniform warmth, a complete dome of ancient light, softly radiant from horizon to horizon. No dark patches, no gaps between constellations, just an unbroken glow permeating the entire sky, the echo of the universe's earliest transparent moment. Embedded in that glow would be tiny variations, temperature differences of roughly 1 part in 100,000, recording the slight density fluctuations in the early cosmos that eventually grew over billions of years into galaxies, clusters, filaments, and all the large-scale structure we see today. The dark sky, observed in microwaves, is not dark. The sky is uniformly completely illuminated. Shift the sensitivity of your imaginary vision into the infrared. Wavelengths just beyond the red end of the visible spectrum, felt by the skin as warmth rather than seen by the eyes as color. The universe reveals an entirely different face. Cool stars, those too faint or too red to catch the eye easily, blaze clearly in infrared. Brown dwarfs, which are failed stars that never gathered quite enough mass to ignite full hydrogen fusion, exist in enormous numbers throughout the galaxy and radiate almost entirely in infrared wavelengths. Vast clouds of gas and dust that appear as dark, featureless patches blocking the stars behind them, invisible light, glow with radiated heat in infrared. Those opaque dark lanes in the Milky Way, which seem to represent absence, reveal themselves in infrared imaging as dense, warm, active regions, churning nurseries where new stars and planetary systems are assembling. And critically, every galaxy at extreme cosmological distance has had its visible light stretched by expansion into infrared wavelengths during transit. The most distant objects the James Webb Space Telescope can observe are not visible in ordinary light at all. Their radiation arrives in the infrared, shifted there by the expansion of space across billions of light-years of travel. In visible light, those regions of sky look empty. In infrared, they are populated with ancient, distant light from the universe's earliest galaxies. Darkness, infrared glow, same direction, completely different universe. Step beyond visible light in the other direction, into wavelengths shorter than violet, carrying more energy per photon, and the universe reveals its most extreme and energetic environments. Ultraviolet observations, made by space telescopes like the Galaxy Evolution Explorer and the Hubble Space Telescope, reveal the hottest, most massive young stars in dazzling intensity. Stars so hot, their surfaces radiate predominantly in ultraviolet wavelengths our eyes entirely miss. Active star-forming regions that appear as soft nebulae in visible light blaze with ultraviolet radiation from the newborn massive stars embedded within them. The universe of stellar birth looks nothing in ultraviolet like it looks to human eyes. X-ray telescopes, instruments like NASA's Chandra X-ray Observatory, which must operate above Earth's atmosphere because X-rays are absorbed by air, observe the universe's most violent environments. The superheated gas spiraling into actively feeding black holes, reaching temperatures of hundreds of millions of degrees and glowing in X-ray wavelengths that human eyes cannot register. The collapsed remnants of massive stars, neutron stars, accelerating, infalling material to extreme temperatures. The vast clouds of gas permeating clusters of galaxies, heated to tens of millions of degrees by the gravitational energy of the clustering process, emitting X-rays throughout the entire cluster volume. In X-ray light, the apparent void between galaxies is filled with glowing diffuse gas. Galaxy clusters, which appear as collections of dim points in visible light, reveal themselves as embedded within enormous extended halos of superheated plasma. The emptiness is full. Gamma-ray telescopes, the Fermi Gamma-ray Space Telescope being among the most significant, observe the most energetic events in the observable universe. Gamma-ray bursts, explosions detected at cosmological distances, lasting from milliseconds to minutes, releasing more energy in that brief interval than the Sun will emit across its entire 10 billion year lifespan, are visible across the observable universe at gamma-ray wavelengths, from directions that appear perfectly dark in visible light. The mergers of neutron star pairs, the jets of supermassive black holes accelerating particles to near the speed of light and launching them across millions of light years. Every one of these events produces radiation that human eyes never register, extend the imaginary sensitivity in the opposite direction, into radio wavelengths, the longest and most penetrating of all electromagnetic radiation. The universe again transforms completely. Pulsars, rapidly spinning neutron stars sweeping beams of radio emission like cosmic lighthouses, completing full rotations in fractions of a second, appear at radio wavelengths in directions that are otherwise quiet in visible light. The enormous jets of energetic material launched by supermassive black holes in the centers of distant galaxies extend for millions of light years in radio emission, far exceeding the visible extent of the galaxies themselves. Cold, neutral hydrogen gas, the raw material from which future stars will eventually assemble, fills the galaxy in diffuse clouds invisible in optical light, but glowing clearly at a specific radio wavelength called the 21 centimeter line, the distinctive radio signature of hydrogen in its ground state. Radio surveys of the sky reveal a richly structured universe of diffuse emission, extended structures, and subtle gradients that visible light shows nothing of. No single observational window captures the whole universe. Radio maps show structures invisible in X-ray. Infrared maps reveal objects absent in ultraviolet. Gamma-ray surveys illuminate events that leave no visible light trace. Every wavelength range reveals a different layer of reality, incompatible with and irreplaceable by every other. The optical sky, the sky human eyes see, is the darkest of all these windows, the most incomplete representation of what actually exists. A single impoverished channel in a universe broadcasting simultaneously across an enormous spectrum. The darkness between the stars is not a property of the universe, not a statement about what the cosmos contains. The darkness between the stars is a property of biological evolution, the specific, narrow sensitivity range that natural selection built into the human retina over millions of years, optimized for navigating a planetary surface by sunlight, not for perceiving the full electromagnetic output of a 13.8 billion-year-old cosmos. The universe is not dark. The universe is silent to us, in the way a symphony is silent to a person who can only detect sounds above 100 kilohertz. The music is playing. Every instrument is active. The darkness is ours. Every direction in the night sky that appears empty to human eyes contains, simultaneously, ancient microwave radiation from the Big Bang's first transparency, infrared heat from cool stars and warm dust clouds, ultraviolet radiation from blazing young stellar populations, X-ray emission from superheated gas and accreting black holes, gamma-ray output from the universe's most violent events, and radio whispers from pulsars and cold hydrogen and the jets of distant supermassive black holes, all of it arriving, all of it present, all of it invisible to human eyes. The gaps between the stars, those dark spaces that seemed at the beginning of this journey to represent emptiness, are full, not slightly occupied, not sparsely populated, full of radiation across the entire electromagnetic spectrum in every direction at every moment. The darkness between the stars is not real darkness. The darkness between the stars is the universe speaking in a language our eyes were never designed to read. And with that understanding in place, every piece of this story can finally be assembled together. We now know why the night sky appears dark, not for one reason, for several, each operating simultaneously, and each revealing something profound about the nature of the universe, its age, its expansion, its acceleration, the biological limits of the instruments we use to observe it. And at the center of all those reasons is something that began as a simple, ancient, almost naive observation, standing in the dark, looking up, noticing that the gaps between the stars were black. Those gaps were never empty. They contained information. They contained history. They contained the universe's entire story, encoded in absence, written in wavelengths we could not read, waiting for the right questions to unlock them. What remains now is to bring all of it together, to stand at the far end of the journey and look back at everything those dark gaps were, the whole time trying to tell us. Those gaps between the stars were never empty. They were always full of information, full of history, full of the universe's own autobiography written in the absence of visible light. Every dark space that human eyes ever registered as nothing has been, this whole time, quietly encoding the age of the cosmos, the rate of its expansion, the architecture of its beginning, and the nature of the laws that govern everything that exists. We began this journey standing beneath a clear, moonless sky, noticing what most people overlook, that darkness is the dominant feature of the night, not the stars, the dark between them. And the question seemed, at first, straightforward. The universe is full of stars. Why is the sky dark? The answer turned out to require dismantling a model of reality that humanity held for centuries, and what replaced it was not merely an explanation for one astronomical curiosity. What replaced it was a portrait of the universe itself, its age, its geometry, its behavior across time, its limits, and its future. Before this story closes, let's step back and look at the full picture, because the darkness we observe in the night sky is not one phenomenon. Several entirely different mechanisms produce what appears, to casual observation, like a single uniform blackness, and separating them is the first step toward understanding what each one is actually saying. The blue sky of daytime is not the universe. The entire glowing dome of daylight overhead is produced by Earth's own atmosphere, by molecules of nitrogen and oxygen, redirecting sunlight in every direction simultaneously. The cosmos behind that atmosphere is not blue. The cosmos behind that atmosphere is not illuminated by daytime. The atmosphere is a painter, a local painter, and what it produces is beautiful and distinctive and tells us a great deal about the composition of our air, but it tells us nothing about the optical background of the universe. The black skies in photographs of astronauts on the moon, in images of spacecraft orbiting Saturn, in pictures of distant planets hanging in apparent emptiness. Those are not measurements of cosmic darkness either. Those are the result of camera exposures calibrated for bright nearby subjects, with a dynamic range too narrow to simultaneously capture sources billions of times fainter in the same frame. Faintness has never been the same as absence. The universe behind those black photographic skies, was always there. Strip both of those away, and what remains is the genuine question: what does the actual optical background of the cosmos look like, and why is it so dark? The most intellectually productive way to understand the real darkness is to follow the chain of failures that preceded its explanation. Each failed attempt revealed something essential: an infinite, eternal, static universe, uniformly filled with stars, predicted a sky blazing at the brightness of a stellar surface in every direction. The mathematics was clear and unambiguous. Every shell of space contributed equal light. Infinite shells produced infinite accumulated brightness. Every line of sight terminated on a stellar disk. The sky should have been as bright as the sun, everywhere, without exception. Dust could not save the classical model. Energy absorbed by dust heats the dust, and heated dust radiates. In an eternal universe receiving uninterrupted starlight without beginning, the dust reaches thermal equilibrium and glows as brightly as the stars whose light it intercepted. The wavelengths shift, the direction scatters, the energy persists. Distance dimming could not save it either. The inverse square law reduces the brightness of each individual star, but the number of stars at any given distance grows by precisely the same factor. The cancellation is exact, not approximate. Dimming with distance is already built into the calculation that produces the paradox. A finite island of stars surrounded by empty space would work mathematically, but every deep sky survey has found galaxies throughout the entire observable volume with no edge, no last galaxy, no boundary where the cosmos stops. Each failed solution revealed the same truth. The classical model was built on three assumptions: an infinite universe, eternal duration, and static geometry, and reality rejects at least two of them decisively. The universe is approximately 13.8 billion years old. That number is not merely a historical curiosity. That number is the reason the sky is dark. Light travels at a fixed, finite speed. The most distant regions of the cosmos have not had time to send their light to us. Their photons are still in transit. Entire shells of space that the classical model assumed to be contributing equal accumulated brightness have contributed nothing yet, because the universe has not existed long enough for their signals to arrive. And crucially, the most distant observable directions do not show us mature, eternally burning stellar populations. They show us younger epochs, smaller galaxies, earlier stages of assembly, and beyond a certain distance, not stars at all, but the cosmic dark ages, and beyond those, an opaque plasma wall through which no electromagnetic signal has ever passed. The accumulated starlight is not infinite. It is bounded by 13.8 billion years of stellar history, and a bounded accumulation, spread across the entire sky, produces precisely the faint dark background we measure. Even the light that has had sufficient time to travel toward us arrives weakened. Space has been expanding throughout the transit, stretching every photon's wavelength, reducing every photon's energy. Ultraviolet light from distant galaxies arrives as infrared, carrying less than it left with. Photons from the most distant observable galaxies are drained of most of their original energy by the expansion that occurred during their 13 billion year journey. The integrated brightness of distant sources is suppressed far beyond what distance alone would predict, and cosmic acceleration, driven by the unknown force cosmologists called dark energy, has created a permanent horizon. Some regions of the universe are receding faster than light, can cross the expanding space between them and us. Signals emitted from those regions today will never arrive, regardless of how long we wait. The darkness for those directions is not temporary. No future waiting, no future instrument, no amount of time resolves it. The darkness in those directions is the universe's final answer. Here is what makes the dark night sky genuinely extraordinary. The darkness overhead is not the absence of information. The darkness is a precise, measurable physical quantity that encodes specific facts about the cosmos, distinguishable from what a different universe would produce. A universe twice as old would have a brighter optical background. Light from regions currently beyond our particle horizon would have had more time to arrive. Today's accumulated starlight would be roughly twice as abundant, the background twice as bright, the sky measurably less dark. A universe without expansion, static, holding every photon at its original wavelength throughout its entire journey, would deliver more distant radiation within the visible range, unredshifted and undimmed by the stretching of space. The optical background would be substantially brighter, a universe with a different stellar history, different rates of star formation at different epochs, different initial mass functions, different proportions of long-lived dim stars versus short-lived bright ones, would produce a different spectral signature in the extragalactic background light. Astronomers can measure that background directly from spacecraft beyond Earth's glowing atmosphere, as the New Horizons probe demonstrated from its position far out in the deep solar system, beyond the contaminating glow of zodiacal dust, and match it against what different cosmological models predict. The measured darkness is a fingerprint of the actual universe, and the darkness will not remain as it is. The sky above us tonight is not the final state of cosmic observation. Every dark gap overhead represents one frame in a story that continues to evolve. Star formation across the cosmos has already peaked. The universe formed stars most prolifically roughly 10 billion years ago, and the rate has been declining ever since. The galaxies we see today are, on average, aging. The most massive and luminous populations of stars burned hot and fast and are gone. What remains increasingly are longer-lived but dimmer stellar populations. The integrated light from distant galaxies is gradually reddening and dimming across cosmic time. Eventually, not soon by any human measure, but inevitable by any cosmic one, the most distant galaxies will cross our event horizon. Their last photons will arrive. Their light will fade from detectability, shifted by extreme redshift into wavelengths no practical instrument can measure. The observable universe will appear to shrink as distant structures disappear from view, not because they cease to exist, but because expansion has permanently severed the communication between them and us. An observer in the far future will see a sparser, dimmer apparent sky, fewer detectable galaxies, less accumulated background light, with no direct observational evidence that the rich large-scale structure we can map today ever existed. The darkness between the stars will be even more complete. The historical record encoded in the night sky will be partially erased. Today's sky, then, is a particular and precious frame. We observe the cosmos at a specific moment in its evolution, old enough to have produced a rich population of galaxies, young enough that many of them remain visible, early enough in the era of dark energy that the large-scale structure has not yet faded below our horizon. Tonight's darkness is not the universe's only possible darkness. Tonight's darkness is a measurement of where the universe currently stands in its own life. The sky appears dark because the universe is young. Not young by human standards, but young in the sense that its clock has been running for a finite time, and that finite time determines a finite accumulation of visible light. The sky appears dark because the universe is expanding. The space through which light travels is not static. Every photon crossing intergalactic distance is being continuously drained of energy by the expansion of the space it moves through, arriving with less than it left with, shifted toward wavelengths that human eyes cannot register. The sky appears dark because the universe is accelerating in its expansion. A permanent horizon surrounds us, sealing off the light from regions whose signals can never arrive, no matter how long the universe continues, and the sky appears dark, in optical wavelengths, to human eyes, because the cosmos is spectrally vast. The universe broadcasts across an electromagnetic spectrum so wide that the narrow window our biology can detect represents a vanishingly small fraction of all the radiation flowing through space at every moment. The sky that appears dark to human eyes is simultaneously glowing in microwaves from the Big Bang, alive with infrared heat from cool stars and warm dust, blazing in ultraviolet from hot young stellar populations, screaming in X-rays from feeding black holes and superheated plasma, and murmuring in radio waves from pulsars and the cold hydrogen gas of future star formation. The darkness is not cosmic. The darkness is biological. This is a good place to simply stop for a moment, not to explain another layer, not to build toward another revelation, just to acknowledge what it means to have followed this question all the way to its answer. Most people who look at the night sky see the stars first. You now see the darkness first, and know what it is. That is not a small thing. That is the universe's own autobiography, read from a single evening's observation by a species of creature that only recently learned to ask the question at all. The darkness overhead is not empty, and you are no longer someone who looks at it and sees nothing. Every dark gap between those stars is a record of how far light has travelled since it left its source, a record of how much space expanded during that transit, a record of what cosmic epochs existed at the distances those directions represent, a record of what the universe was doing while the light was on its way. The darkness between the stars is not the absence of the universe. The darkness between the stars is the universe's history, resting between the stars. The darkness between those stars is the same as it always was. Not a single gap has moved. Not one dark patch overhead has been filled or altered by anything you learned tonight. But the person looking at it has changed. The next time you find yourself outside on a clear night, the next time your eyes drift upward and settle on those spaces between the visible stars, you will carry something you did not have before. You will know those gaps are not empty. You will know they hold the universe's age, its expansion. Every second that passed between the Big Bang and tonight, written in the apparent absence of light. The darkness overhead is not nothing. It never was. Thank you for staying through all of it. For following a question most people never think to ask, all the way to an answer most people never expect. If this journey meant something to you, a like and a subscribe are how you let me know, and how we find each other again for the next one. Take a moment tonight. Step outside if you can. Look up at the dark. You'll see it differently now.